Good morning, good afternoon, and a huge welcome to ARA's Webinar Wednesday program. My name is Jerry DiMaggio. I'll be serving as moderator for today's webinar, which is entitled Mechanistic Analysis of Asphalt Rutting in Airfield Pavements Using Viscoplastic Shift Model. Next slide. I'd like to first cover a few housekeeping items with you. First of all, in slide number 2, if you're experiencing a issue related to sound and you're using your computer speakers, disconnect from the speakers and dial in using your phone. If you continue to have another issue, please use a chat button and send a message, but send that message only to the host, please. Next slide. We encourage you to ask questions throughout the entire technical program, but all questions will be addressed at the conclusion of today's technical webinar. If you have questions, and listen carefully, please click on the Q&A button and send your question, and we will address it in the Q&A session directly following the presentation, but send your question only to the host and the panelists. Again, only to the host and the panelists, please. Next slide, please. Finally, to view the presentation in full screen mode, at the top of your webinar settings, as you can see in slide number 4, click on the down arrow, highlight View, and then choose Fit to Viewer. Just a reminder, and I'll cover this again at the conclusion of the technical program, in order to receive a 1-hour PDH certificate, you must attend the full 1-hour webinar. Additional information regarding that certificate and a copy of today's presentation will be presented at the conclusion of the technical program. Next slide, please. Now it's my great pleasure to introduce our presenter for today, Dr. Ghassan Chehab. And Ghassan is currently a principal civil engineer within the Research and Technology Deployment Group of Applied Research. He received his PhD in Civil and Environmental Engineering from North Carolina State University. Has over 25 years of experience serving as an academic, researcher, and technical consultant in the areas of pavement engineering and materials. Notable accomplishments, including the many that he has, is he established a pavement engineering program at the American University of Beirut, where he introduced 5 courses in pavement engineering, management, construction materials, and completely developed the asphalt laboratory for that institution. That laboratory is considered to be the premier laboratory throughout the Middle East. He supervised 25 master's candidates and 4 PhD students during his 15-year tenure at that location. Ghassan is considered an expert in advancing modeling of asphalt mixtures, recycled and byproduct materials, road and airport engineering, energy harvesting. I'm not sure I personally understand that completely, but I'm sure he could educate you. That's not the topic of today's webinar, however. Ghassan has finally been the author or the co-author of more than 150 journal papers and several textbook chapters. It's my great pleasure to turn the program over to Ghassan, my good friend and colleague.
Thank you, Jerry, very much for your presentation, comprehensive presentation. I would like to talk today about the topic of rutting in airfield pavements and what are the factors really that cause rutting in airfield pavements. Life is full of successes, and we have seen, fortunately, a lot of successes in pavement engineering, whether applied to highway pavements or applied to airfield pavements. And that's because of the advancement in technology, state-of-the-art now research in asphalt binders, asphalt mixtures, pavement design, construction, quality control, quality assurance, development of performance-based specifications, and whatnot. But like the successes we see, we also see failures, and it's not a shame. Failures do happen. And it's important to acknowledge them, learn from them, and see how we can avoid them in the future. What you see in the pictures are depressions or dips in the pavement that we call rutting, and they happen basically under the wheel path of a truck or a gear of an airplane. So again, you see more failures here, and thus you could tell that the scope of this the study here is the rutting in airfield pavements, particularly airfield pavements that witness very heavy traffic volume, heavy airplanes as well. So we're talking about large airports, hub airports, and we want to see what causes these ruttings. So failure is success if we learn from it. This is not me speaking, this is Forbes. And in that spirit, the question that poses itself is, why are some airfields with proper asphalt or binder grade and proper asphalt mixture design for the pavement surface layers experiencing asphalt rutting? What are we doing wrong? So let's concentrate on those failures and investigate them and understand the three W's. What went wrong, where did it go wrong, and why it went wrong. So I'm going to start with the background and the motivation behind this study and the objective that I am pursuing. And beginning and talking about the scope of the study and the methodology that I adopted in achieving my objective. First talk about material characterization models. We need to characterize how the asphalt mixtures behave and perform under various climatic conditions versus various loading conditions and so forth. And then once we develop these models and incorporate them into software packages that predict the performance of a pavement, we want to focus on what are the factors that affect asphalt rutting. And then after we do that, we'll try to predict asphalt rutting for actual airports, actual airfields, for actual mixes, actual aircraft that land and take off from there, and compare it with the measured rutting from the field from that airport, and see how valid, how accurate are our models and our simulation from the software. It's called FlexPave, and we will talk about that later on. And then finally, we'll come up with the conclusions from the study and recommendations as how to avert or avoid such failures in the future. And what I'm talking about is not a coincidence. It's not that we've seen rutting in one or two large airports. It's seen in a variety of airports across the world. Now, we don't maybe hear about them a lot because they have to be fixed very quickly, because it's very critical to make a runway always operational. But still, there are a lot of airports across the world that do see and do witness rutting. Recently, a high-profile airport, that takes very heavy aircraft traffic, very heavy aircrafts, witnessed up to 70 millimeters, almost 3 inches of rutting just after opening the airport to traffic. Of course, one would suspect that high tire pressure from the aircraft are causing that, soft binder used in the top layer, the slow traffic from the airplanes as they wait for their turn to take off, and maybe these airports are in a very hot climate, making the surface layer soft and thus leading to rutting. All these are legitimate factors that affect and impact rutting, but we don't know to what extent they impact rutting and whether they're the only factors that impact rutting, and that's what we're trying to investigate in this study. In the SuperPave binder specifications for highway applications, it's stipulated that if you have slow traffic, you need to bump the PG grade by 1. And that means your binder needs to be stiffer because of the slow traffic. And when you bump it by 1 grade, as if you're saying that the temperature of the pavement is higher by 6 degrees Celsius. So the binder has to be stiff enough to take that extra 6 degrees Celsius that's higher. If you have stopping traffic, you need to bump the performance grade of the binder by 2 grades. by 12 degrees Celsius. Now, this is for highway applications, and the common practice is to just grade bump only the surface layers. So we don't really bump the grade of the layers below the surface layer, the layer at the top of the pavement. And these lower layers, whether we call them base layers or binder layers, really don't experience as high a temperature as the surface layer. And thus we tend to not to ignore bumping the grade. And we also try to minimize the cost of the project. So we try not to bump the grade, because bumping the grade entails modifying the asphalt with polymers or acids, so it just becomes expensive. So to come up with a lower cost in the pavement construction, we don't bump the grade of lower layers, mainly base layers, also called the binder layer. That's for highways. For airfields, there are specifications for civilian airfields that are set by the FAA, particularly for asphalt mixtures. In the circulars, we look at item P401 for asphalt mixtures. For military airfield specs, the DoD, sets these specifications. Now, in the FAA specifications version G, it stipulates verbatim that typically rutting is not a problem for airports. Grade bumping, however, should be applied for the top 1.5 millimeter or 5 inches of paving at locations where stacking is expected, at the ends of runways and taxiways. So FAA does acknowledge that, yes, also in airports, we need to bump the grade, but only for the top 125 millimeters. I'm sorry, I'm always going backwards in my slides. Now, in version H of item P401, the bumping now is not a function of depth. It's a function of the gross weight of the aircraft. So depending on the weight of the aircraft, depending on the pavement type, maybe whether it's a regular part of the airport that's not too important, or if it is part of the airport that witnesses stationary traffic or slow traffic, those dictate what the bumping of the grade is. So for example, for a very heavy aircraft, let's say 777-300, and that is waiting on a taxiway, that area needs to be bumped by 3 grades. However, there's no mention to the depth to which the PG grade bumping is recommended. They just say that you need to bump the grade, but how deep? 100 millimeters, 200 millimeters, 50 millimeters. So that's what was missing. Now, designing the airfield pavement is similar pretty much to designing a highway pavement, where the common approach is to follow a multi-layered pavement design. The surface layer is the stiffest, followed by lower layers that are softer. However, contrary to the French approach, where the layer is the surface layer, the base layer or the layer below the surface layer are stiffer. Now, there are challenges and complex loading mechanisms in airfield pavement design. And not only, some of which are the large gross weights and tire pressures, the wide range of traffic speeds on a runway or a taxiway, and the channelized traffic of the airplane. They all pretty much land at the same spot, particularly with the adoption of the ILS, the Instrumented Landing Systems. Now, the Airfield Asphalt Pavement Technology Program did release 2 projects. The 2 projects, the objective which was to incorporate aircraft tire pressure as a factor in whether we should make the pavement surface layer stiffer or not. And another project also looked at, should we modify the high temperature PG grade or bump the binder grade for deeper layers or not. So the objective now is to investigate asphalt rutting failures that are not caused by inadequate asphalt mixture properties in the surface layer, by considering possible contribution of the asphalt mixture properties of the base layer. And again, when I say base layer, that's the second layer or the layers underneath the surface layer or the top layer. So if the surface layer has been designed well and the mixed properties are well chosen and tested. How about the base layer? Could the base layer properties lead to the rutting failures that we are witnessing or not? Uh, so exploring whether these base layer properties are affecting rutting or not, we need to do a mechanistic analysis, just basic solid mechanics analysis, but using a software that is a 3D. It's called FlexPave. It's a 3D nonlinear finite element software. It performs mechanistic performance analysis. It incorporates viscoelastic continuum damage models for fatigue cracking. So there's nonlinear and fatigue models in there. It incorporates the viscoplastic now, the compressive rutting strains, the viscoplastic shift model for rutting stresses. It also deals with layered viscoelastic solutions for thermal stresses and thermal cracking, and it does incorporate moving loads and at various speeds. It also incorporates the various climates through the enhanced integrated climatic module. Now, the software has been developed by Dr. Richard Kim at North Carolina State University. Whenever we want to do the mechanistic analysis, we need to know what are the factors that we need to look at and evaluate. Three important factors are the compressive stresses that the airplanes impart on the pavement surface, the loading time or the speed of the aircraft, how much time is that weight being applied on the pavement, and what is the pavement temperature. So we need to evaluate these three factors in our analysis. We also need to look at what is the gear configuration. There are various airplanes with various gears. We're going to look at the gears of a 777-300, basically a tridem axles. We're going to look at the gear of an Airbus 320. We're going to compare those to an 80 kilonewton easel of a truck to see the impact of the gear configuration, the axles on the rutting from the base layer. We're also going to look at traffic speeds. What we will do is we will evaluate the rutting due to three different speeds: 5 meters per second, 10 meters per second, and 30 meters per second. 5 and 10 meters per second are witnessed on taxiways. 30 meters per second is experienced on a runway. So we need to configure to evaluate all these different criteria in our analysis to see which ones are really impacting the rutting and not. Looking at the characterization, what we're going to do is, for the analysis, we need to have asphalt mixtures to incorporate or to include in our characterization. So what we did is we went to a real actual airport that witnessed rutting. Some of that rutting was significant. So it's a real case study, it's a real case, a real airport. And we got three asphalt mixtures that were used in that airport. So we got a surface mix, a mix that was put on the surface, we call it mixture A. We got two different base mixes that were put in the base layer. One is stiffer than the other. One is performance grade 70, the other is performance grade 64. So as you see, the dashed orange line here is a stiffer mix than the purple dotted line. What we are seeing here, these curves are the complex modulus or dynamic modulus, or the stiffness, let's say, of a viscoelastic material of these mixes as a function of frequency. So we measure as a function of frequency the modulus of these mixtures and the complex modulus as a function of frequency, but we later convert it to relaxation modulus as a function of time, and that is needed because of the modeling in the software. So we convert it to relaxation modulus or the modulus that is a function of loading time. All these mixes that we brought and we sampled are compliant. We found that they are compliant with FAA P401. Now, the viscoplastic shift model that we're going to use in the FlexPave software, our mechanistic analysis, utilizes the SSR test, or the stress sweep rutting test, which we'll be talking about later. And that test is conducted for various theoretic stress levels, various loading times, various temperatures, and we obtain the viscoplastic strain data at these different conditions. We then make use of the time temperature superposition principle with growing damage and the time stress superposition principle. From these principles, from the SSR tests, we developed the viscoplastic strain master curve. That viscoplastic strain master curve at reference conditions, at a specific temperature, at a specific stress, it can tell me exactly what is the strain for any number of cycles of these conditions. So what is this SSR test? The SSR test was developed for highway conditions. It's AASHTO TP134-19. What it is we run sinusoidal blocks of sinusoidal loadings at two temperatures, T high and T low. Both these temperatures are a function of the climatic zone and the PG grade. So we're going to run the test repeated for two different temperatures. We run three different blocks of sinusoidal waves. Each block consists of 200 cycles, 0.4 loading second, 0.4 seconds of loading time, and 3.6 seconds of rest period to allow any recoverable strain to recover. We load at 200 cycles at 100 psi, 200 cycles at 70 psi, 200 cycles at 130 psi, and we measure, of course, the strains from these loading blocks. We also apply confining pressure of 10 psi. The Victoria stresses, the confining stress, are all basically obtained from an analysis, finite element analysis, that simulates the conditions of stress and strain states under a truck traffic of a highway condition. Now, for airfield conditions, aircraft tire pressure is higher and the load is heavier. So instead of the typical load we just saw, we increase the vertical stress by 100 psi and the confining pressure by 20 psi, and we repeat the SSR test. The shift model now, we talked about the SSR tests. We do have the viscoplastic strain measure. We do have the time temperature superposition principle available, so we can find what we call the reduced load time shift factor, or the time temperature shift factor. We can also find the time stress shift factor. Finally, I'm not going to go too much into the equations, but the formulation of the viscoplastic shift model basically allows you to calculate for any reduced number of cycles the viscoplastic strain. And what I mean by reduced number of cycles, it is the number of cycles at a specific reference temperature and stress. So for a given temperature and stress, I can know what the viscoplastic strain is for a reduced number of cycles. Now, because of the applicability of time temperature superposition and time stress superposition, I can then know what is the viscoplastic strain at any number of cycles for any temperature for any stress. And that's the power of the shift model. Now, the shift model does have coefficient or fitting parameters that we need to determine, and we can determine those from the SSR test. If we use these mixes, if we use these mixes with, I'm not sure why it's moving by itself. Okay, sorry about that. Okay, so we're gonna conduct the SSR test for these mixes that we obtained from the airport: surface mix A and the binder mix or the base layer mix C, which is a soft one. And we're gonna conduct it at the high temperature and at the low temperature for the pavement structure at hand, and for the Dallas climate. And the Dallas climate of Dallas, Texas, is similar to the climate of the airport that we are dealing with. And as you can see here, the permanent deformation that we got from the SSR test for the surface mix are overlapping and they're close for 7 replicates. We also tested for 7 replicates the samples for the binder mix C, and you can see that the rutting is higher because of the softer binder, and there is more variability. That's at T high. Same as at T low. I'm not sure how to, I think my mouse is not functioning well. At T low, we figure we see the same thing. Good match between the replicates for the surface mix, but a lot of variability, not a lot of variability, but expected variability in the binder mix specimens because of the poor construction that was witnessed, poor materials that were used, and the large aggregate size. So we predicted the the strains, the viscoplastic strains, 47 replicates at T high and T low, and we compared them to the measured strains. And you see how the predicted strain and the measured strain overlap, both for the surface mix and binder mix. And that tells me that the SSR test with the shift model are predicting the viscoplastic strain correctly, similar to what the specimens are being deformed by. So that gives us power and confidence with the SSR test and the shift model that they are predicting the correct viscoplastic strain for mixes under certain loading conditions, certain temperatures, and certain frequencies in loading. And so here what you see is I have now the Prony series coefficients of the relaxation modulus needed to model the asphalt concrete or the asphalt mixture in a linear viscoelastic state. For the nonlinear viscoplastic state, the shift model is also developed for both the surface layers, and in here is the surface layer, and the base layer or binder layer C. These are the coefficients of the shift model. So now I have fully characterized my mixes in both linear viscoelastic range and the viscoplastic range. So what are the factors affecting my rutting now? Again, using these mixes from the airport, you see the mixes basically. I will take a reference scenario. I will say, let me do the analysis for rutting using, first of all, a reference scenario, which is a B777-300. I will assume I have one layer that's 40 centimeters thick in my pavement structure. It comprises mix type A, and it is for a speed of 10 meters per second. The aircraft speed is at 10 meters per second. That's my control case. To know what the effect of the gear type is, I keep all the other factors constant. I only change the gear, and I replace the gear of the 777 by a gear of the A320, and I try one single easel, and thus I can see what the effect of the gear type is. I also want to witness what is the effect of speed of the aircraft. So keeping everything constant, I only change the speed. I go slower to 5 meters per second and faster at 30 meters per second to see the effect of speed on rutting. I also want to see what is the effect of having multiple asphalt layers instead of one, and what is the effect of having mixes of different stiffnesses on rutting. So in one case, what I do is I use, for the same 40 centimeter, instead of mix A, I use mix B, which is softer. And then what I do is, everything held constant, I divide that 40 centimeter layer into two layers: a surface layer, 15 centimeter, and base layer, 25 centimeter thick. I use mixes A and B respectively, and then I use mixes A and C respectively to see what is the impact of having two different mixes on rutting. So what the software output is, basically, what it tells me is, before going to the output from the software, we know that the compressive stress imparted by an 80 kilonewton axle is 800 kPa, around 800 kPa at the surface. Now that imparted by an Airbus A320 and 777 are much higher. They go up to 1,400, 1,600 kPa. Now these are at the surface. So I know at the surface I have higher pressure from aircraft. But what about deep in the mixture? I see that 800 kp, the 1,400, 1,600 kPa at the surface, it goes down to 800 kPa only at 18 centimeter for the A320 and 21 centimeter for 777, meaning that 800 kPa that I'm worried about and that I designed for and pick my binder and mixture for at the surface, I need to consider the same conditions and the same specifications and recommendations for in airfields deep down in the pavement. So that 800 kPa is occurring at about 20 centimeters of the pavement. So at 20 centimeters deep in airfield, I'm still witnessing high compressive stresses. And what I do at the surface for highways, I need to do a deep down in the base layers now for the aircraft, because 20 centimeter, I'm pretty much going into the base layer and leaving the surface layer. So that tells me there's high compressive stress even in the base layer in airfields. And what is the effect of the gear type? So for an 80 kilonewton easel, I know that, sorry, the loading time is only 0.2 seconds at the surface. However, the loading time of an A320, because of its gear type, is 0.05 seconds. It's 0.07 seconds for 777. So it takes much more time for 777 to pass over a certain point in the asphalt. If I go that to the depth of 30 centimeters, an 80 kilonewton easel's load is felt for 0.2 seconds. And however, for a 777 at the same depth, the load is felt for 0.6 seconds. So the loading time at 30 centimeters is felt for a much longer period of time. And the longer the loading is felt, the softer the mix becomes. That because it's viscoelastic. Longer loading time means slower speed means the mixture itself is gonna become softer. So at 30 centimeters deep, I'm in the base layer. So the base layer now is becoming softer just because of the gear type. Now, what is the effect of speed? So for the 777 gear, if I take the example of 5 meters per second is slow speed versus a fast speed of 30 meters per second, what I see is that at 0 centimeter at the surface layer, load is being felt for 0.12 seconds versus only 0.02 seconds for 30 meters per second. So the load is felt for a longer time, of course, 45 meters per second. But again, I'm interested in deep in the base layer. In the base layer, 30 centimeter deep, the load from the 5 meters per second lasts 0.8 seconds. And it's only 750 kp, sorry, it's 750 kPa. For a faster speed, the load is only felt for 0.15 seconds, much shorter duration of loading. And the stress is lower. So when I go for higher speeds, I only feel the load for a lower duration of time versus higher duration of time for a slow speed. That tells me again that longer loading time means the asphalt in the base layer is going to be softer if I have a slow moving aircraft. What about temperature, pavement temperature? Now the pavement temperature at the surface is the highest. Again, taking a hot day in Dallas, Texas, 3 a.m. in the morning, temperature could be about 25 C. It goes up to 65 C at 3 o'clock in the afternoon. So there's 42 C difference between 3 a.m. and 3 p.m. Of course, that's pavement temperature in Celsius. Now, rutting is going to happen at high temperature. So let's say it's going to happen between 40 degrees C and 65 degrees C. So basically, between noontime or morning time and the afternoon time is where I'm going to see hot temperatures causing rutting. However, if I can go deeper now, if I go deep to 35 centimeters, where I have the base layer, temperature now is constant regardless of what time it is in the day. And the temperature is not very low. I mean, it's just less than 40 degrees C. That is enough to cause rutting. So I have a temperature that is lasting all 24 hours. That temperature is high enough to cause rutting in the base layer. So I have about 40 degrees C for it's consistently high temperature as I go to the base layer. Of course, it's not as high as the surface layer, but the surface, that hot temperature is only applied for a short period of time. Okay, lower, shorter than in the base layer. So the base layer is feeling high temperature. Again, that high temperature is making it be softer. So I have three effects now: gear type, speed, and temperature, all contributing to softness in the base layer. So if I look at, sorry, the effect of gear type on the compressive strain, where is the strain, the compressive strain between the difference in compressive strain between a 777 and an easel, let's say, where is it maximum? What I found out is that 15 centimeter deep in the pavement, I see the biggest difference in compressive strain. So that difference between 777 and an easel, the compressive strain difference because of gear type is felt at 15 centimeter deep. So that's deep in the pavement. So the compressive stress, the compressive strain difference is not felt at the surface. It's felt deep down in the 6 inches down deep in the pavement. So I need to be careful here when I'm designing and when I'm choosing the mix for deep down. If I look at the effect of speed of loading time, a 30 meter per second, a 5 meter per second moving load gives me a strain that's twice as much as a 30 meter per second, but that's the maximum difference. So the maximum difference due to the slow speed is felt at 25 centimeter deep, again in the base layer, not at the top, not at the surface. If I look at the effect of a soft mix versus a stiff mix, again taking a stiff base layer, which is mix B that we got from the airport, versus mix C, which is softer, the difference is twice in the strain. So the softer is giving me twice the strain as a stiff mix, and that is felt at 20 centimeter deep. That's the maximum magnitude in strain, and 20 centimeter pretty much in the base layer as well. So these differences in due to gear type, speed, and temperature are felt deep down in the pavement, not at the surface layer. So I can calculate now what is the viscoplastic strain for a 777 for a different for a certain loading, temperature, and of course a gear type. But in any given airport, and at the airport of study now of interest, there's no only 777s landing and taking off. There are a variety of aircraft that are using that airport. And each of these aircraft, let's say you have A320, A330, A350, 777, Boeing 787, all of them have different wheel spacing, different tire pressures, different axle spacing, different loads. So each one is causing different damage than the other. So how am I going for that airport? How am I going to calculate the total damage from this combination of aircraft? I can calculate it for one, but how am I going to calculate for a mix of aircraft? Each one has a different amount of planes taking off and taking down. Let's take an example of that airport and just take the wide body aircraft, code E aircraft. So spanning from A330, A350, 777, 787, A340. Again, taking the 777 as a control and saying, and it's basically most of the airplanes that land in that airport are 777. 17.6% of my aircraft are a 777. That's the share of total movements. Let's say this 777 causes a certain damage, and that damage is 100% to normalize it. And that's the orange line here. Now, all the other wide body aircraft are causing similar damages, and the A320 is causing significantly lower damage than the 777. So, taking these wide body aircrafts, I calculate the damage due to each of these aircrafts using FlexPave. And then what I do is to combine their effect. I follow the same approach that I follow in highways, where I convert the effect of various trucks to the effect of a single easel, 80 kilonewton axle. I convert the damage of each aircraft to the damage of the 777. And that I find out that that damage is about 90% for the different airplanes, about 90% of the damage that a 777 causes. So what I do is I divide that damage by that ratio of damage. That's I'm gonna call it the equivalent gear factor. Instead of equivalent axle load factor, an equivalent gear factor. And now I can combine and accumulate the damages of all these aircraft into the damage of one single equivalent gear. Multiplying the share of the total movements by the equivalent gear factor, I get the total equivalent gears that are landing every day in that airport. And thus now I can predict what the rutting is each day due to the realistic aircraft that are landing. So everything is realistic here. The mixes are realistic, the amount of aircraft, the type of aircraft are all realistic. And I'm calculating and trying to predict the damage that it causes. And this is what you will see here. So in FlexPave now, what I've done is we've tried to predict the rutting in that airport. When we visited that airport, we saw there are, for different areas in the airport, runway 1 versus taxiway 1, there are different magnitudes of rutting. What you see here is the red asterisk, and that's the maximum rut that was witnessed in runway 1. The asterisk or symbol that is in green is the smallest rutting that we saw in runway 1. So let's try to predict now the viscoplastic strain, or the rutting actually, the rutting using FlexPave and a shift model for that airport. Using what I've done, we took cores next to the areas that rutted the most, which is here near the what I like 1 centimeter here, where that red asterisk is. That mix, because this is high, that mix I'm gonna call, for example, a fair mix. But then I go to the places where rutting was minimal, and I take a core. From that core, I extract the mixes and do the test on them and predict the strains. And what I found out that for the same mix, for example, for the good mix, the mix that is in blue at 100 meters per second, I see very, very minimum rutting. Very similar to the rutting that we witnessed and measured. Now, if that same mix is, sorry, for aircraft traveling at 30 meters per second, at areas where I see minimum rutting, I get that much of rutting predicted. But again, it is close to the minimum rut that I got. If I go to a fair mix, the predicted rutting is higher and becomes closer now to the maximum rut that I measured. So the nice thing about this is, for the mixes that we extracted from the airport, the predicted rutting is between the range of the worst rut that I measured in runway 1 and the least rutting I measured in runway 1. And that's very good. If I go to taxiway 1, we have a fair mix and a poor mix. The poor mix was next to areas that had very high rutting, 2 centimeters of rutting. So I predicted the viscoplastic, I predicted the rut depth for that poor mix, and again, it's close to the worst mixes seen in taxiway 1. Whereas for a fair mix, at 15 meters per second, I saw rutting that is close to the best or the least ruts I found in taxiway 1. And again, the predictions of rutting fall in the range of the least rut and the maximum rut measured in taxiway 1. And that's very realistic. And that was at year 1, that was at year 4. We didn't get more points. I don't think we're gonna get more points because I think they fixed the taxiway. Going to taxiway 2, again, I do the prediction. The prediction of rutting falls within the range of ruts that are seen on taxiway 2. Going to taxiway 3, again, what I do is I use a very good mix or a good mix, and its prediction is close to the small ruts that are measured. I use a fair mix. Now, the rutting for the fair mix at year 1 matches the worst rutting measured, but at year 4, my predicted rutting is higher than the worst rutting that was measured. But in all, my predicted rutting from the actual mixes obtained from cores next to the measured rut are close and within the range of rutting in that airfield element. What are the conclusions and recommendations? So the takeaways are the following. Deeper layers in an airfield are subjected to high compressive stresses. Unlike highways, they are subjected to significantly high compressive stresses that need to be taken into account. These compressive stresses in deeper layers are applied for considerably longer loading times compared with the loading times at the surface. So that longer loading times makes the base layers softer and softer. That needs to be taken into consideration because it does lead to rutting. Temperatures in the deeper layers are high, not as high as the surface, but they're high enough, and they are applied for an extended durations, unlike the surface. And again, that high temperature for a long extended duration makes the asphalt, the base layer, softer and softer as well. That contributes to rutting. What we did is we used FlexPave now for a variety of aircraft speeds, aircraft types, airfield elements, different properties of the materials, and we did so many simulations, and we got a graphical conclusion. And hopefully, if you take anything out of this presentation, you kind of always remember this snapshot that for all the conditions together, if we average all the rut depths that were obtained, 70 to 80% of the ruts were obtained from the base layer. Only about 20% of the rutting in airfields were obtained from the surface layer. We emphasize the surface layer so much. We bump their grades, we make very stringent quality control, quality assurance, but sometimes we don't put as much importance to the base layer, whether in the quality of the material, type of material, or the quality of construction. However, the rutting from the base layer is significant. That's where the rutting in the airfields that were visited were also seen from ditches that were from pits that were cut, from cores that were taken. Most of the rutting that was witnessed did come from the base layer. So what is predicted in FlexPave, what is seen in real pavements of the airfield, it is the base layer that is giving the rutting seen at the surface. The final thought I want to leave with you, depending on the mix we choose for the base layer, depending on the temperature and the location, taxiway versus runway, rutting from the base layer can exceed that from the surface layer. The stiffness of the deep asphalt layers are critical for asphalt rutting in airfields. So stiffness needs to be taken into account very carefully. And the results do warrant revisiting the PG grade pumping recommendations for airfields to address deep asphalt layers. So maybe we need to emphasize that deep asphalt layers do require PG grade pumping. We need to stiffen up the binder. We need to stiffen up the mixes of base layers in airfield pavements. I do want to acknowledge Dr. Richard Kim from NCSU for his help in FlexPave and the shift model, Dr. Hussein Qasim and Ms. Yara Hamdar who helped in this presentation and study. And finally, the study wouldn't have been completed without that research and work that done from the office and from feeling the heat by going to the airfield and witnessing everything firsthand. And I thank you for listening to this presentation. Jerry?
Sorry. Thank you, Ghassan. Very interesting. Good delivery. Next slide, please. We'll get to the Q&A program momentarily. We just wanted to share some of the up-and-coming webinars with you. Remember, this is really about the 3.5-year anniversary of our program. It's a monthly program. All of our presenters are ARA employees. On August 31st, we'll be hearing from Brandon, and Brandon will be speaking to geostatistical methods of estimating values of interest at unsampled locations. He's a senior civil engineer with ARA. And then in late September, we'll be hearing from Vanessa Napoli, and we'll be turning our attention to underground utilities, often a problematic issue in designing construction and preservation projects. Vanessa's presentation is non-destructive evaluation technologies for detecting utilities. It's largely based on a project that ARA just completed for the Federal Highway Administration. So we currently have programs planned through November, and we intend to continue the series beyond that. We invite you to join us, and we have a diverse suite of topics, as you can tell if you've joined us for the last 3.5 years periodically or consistently. Next slide, please. Okay, I'd like to now get to the Q&A program, and we do have a number of questions. We've got a limited amount of time, and I want to remind everybody we kind of devote this period of time only to Q&As here. I know you know all how to send emails, but this is not a workshop. It's really a webinar. So sticking with that, first question for you, Ghassan, is why you're running, and I'll paraphrase a bit here, why are running profiles predicted for surface mixes matching well, while those for the binder mixers don't appear to match as well?
Yes, well, for binder mixes, typically, we have larger aggregates in the mix, and that by itself increases the variability. Also, the variability is, I think the variability is higher also because there was soft binder and poor binder material that was used after we extracted it and tested it. So that has given that poor variability seen in the binder layer and the difficulty in matching it properly.
Okay, thank you. And I failed to mention that first question was from Alice. Next question is from Jamal. And Jamal would like to know, what is the difference between FlexPave and MEPDG, since both of those can predict rutting and can be used for highways?
Yeah, the MEPDG, also known now as the pavement ME or the mechanistic empirical pavement design, has been developed for highways, and the models for predicting the performance are empirical, and these models are calibrated for highway conditions. FlexPave, however, is mechanistic, it's not empirical, so really it doesn't depend on the type of the load that's applied. It works for any type of load. There's no calibration there in calculating the viscoplastic strains or in the viscoelastic strains. So it's a mechanistic analysis. So it works better for aircrafts and highways and trucks in the same way. Unlike the MEPDG, that's only restricted for the type of trucks that the models were calibrated for.
Okay, thank you. So the next question comes to us from Jason, and Jason wants to know why you didn't consider an Airbus 380 since it has a higher load than a Boeing 777.
Excellent question. The A380 is heavier than the 777. However, it has more gears, and thus the load per tire or per gear is less than the load per gear for a 777. And what's critical really for the pavement is not the overall load of the aircraft, it's the load imparted at a certain location by the gear. So the 777, does have the highest contact pressure with the pavement, and that's why it is looked at as the most critical for airfield pavements.
Okay, thank you. Got a series of questions. I'll try to get to several of them, and I apologize for this person's, I'll mispronounce the name, Ehab. And I'll paraphrase his first question. I understand you considered the effects of load, speed, depth, and temperature on rutting behavior in mixes. However, given the high speed at landing airplanes, it's a long question, bear with me. Would you not expect rutting due to braking shears to play a more crucial role in creating the ruts?
Yes. So now at the high speeds during landing on the runway, high speeds make the asphalt stiffer and stiffer because the loading time is less and less. So there's no rutting expected at the landing position. There is rutting expected at the takeoff position where the aircraft, is preparing for takeoff. Now, yes, there is rutting at due to shear at turning loop positions. For example, as the airplane is exiting the runway to a taxiway, there is shear load there at the surface. That considers the surface deformation and not really the rutting in the base. So they're two separate phenomena, and they're not combined together. You see different types of deformations at the surface when you look at them.
So next question, also from my good friend whose name I can't pronounce well, so I won't butcher it again. And the question is, do the taxis you discussed receive the same amount of acceleration and deceleration at landing?
Well, the airplanes don't land on the taxiway, but I'm assuming they're talking about moving over the taxiway, and the answer is no. That's why we took taxiway 1, taxiway 2, taxiway 3, and because of the different speeds on these taxiways, some taxiways had to be removed, and some taxiways needed to be repaired. Some taxiways didn't see any rutting because of the speed that our friend, who asked the question, talked about. So yes, different speeds on the taxiways do yield different rut depth, and that's why I put 3 examples here in the slides.
Okay, last question we can fit in from a time constraint point of view. Have you considered temperature gradient in the FE models, surface layer temperatures being different from base temperatures?
Yes, so that was considered. So there was a study to look at the gradient of temperature from the top to the bottom, and that's how the prediction was done. That's how we came up with these temperature profiles. It's from a field study that, for various locations, especially at locations similar in climate to the one at the airport. So the answer is yes.
Okay, I'm going to move on. We got two more slides to share with you. It's about all the time we have for questions, but I want to remind everybody, Ghassan has been gracious to give us his email address. Please follow up if we didn't get to your question. So all of you who joined today for the entire hour are entitled to receive one PDH hour certificate and a PDF copy of today's presentation. Please allow 3 weeks for you to receive your certificate, and you could download that PDF presentation at our site, again, within about 3 weeks. And feel free to contact us, ARA Webinar at ARA.com, if you have any questions. We invite you to register for the future programs. Again, all these programs are recorded, so within a week or two, maybe 3 at most, you see them on the site that you see on slide number 60. Next slide, please, the last slide. ARA is a fabulous company. I'm on my third career, federal government, national academies, and now 9 years at ARA. We are always striving to find great people to join our team. We're about 1,600 strong, about 45 to 50 offices, depending on how we count them. If you're interested in current employment opportunities with ARA's Transportation and Infrastructure offices, which is one of our 5 business sectors, please send a brief resume and contact information to the address that you see on this slide. I want to thank you all for your attention. Thank Ghassan again for an excellent presentation, fantastic delivery. You all have a blessed day. Thank you very much. We'll see you next month.
Thank you, Jay.